Hello everyone. In this video we return to the first model we created earlier in the course. The last time we worked with it, the model represented a very simple building, a basic box consisting of a single space and one thermal zone. At that stage, no space type had been assigned and no HVAC system was included. As a result, the indoor temperature was influenced only by heat transfer through the building envelope and the outdoor conditions. In this exercise, we will begin transforming that basic model into a more realistic representation by defining a space type and applying internal loads. To make the example more relatable, we will assume the space is used as a small office occupied by a single person. We will also take the next step and explore how to provide a basic level of thermal conditioning. Go ahead and open the most recent saved version of that model, and we will start building on it together. Open the model and navigate to the Schedules tab. Click the plus button to create a new schedule set and give it an appropriate name, such as Office Schedule Set. For now, leave the set empty and move to the Schedules sub-tab to create the individual schedules that will later be assigned to this set. Use the plus button again to create new rule set schedules. A dialog window will appear where you select the type of schedule you want to create. First, create an activity type schedule for the activity level. Then create a fraction schedule for occupancy, and make sure to give both schedules clear and meaningful names. Once the schedules are created, they must be edited. Select one of the schedule objects. Each rule set schedule contains profiles for summer design day, winter design day, and a default run period profile. For this workflow, ignore the design day profiles and focus on the default run period profile, indicated by a light blue marker. Selecting this activates the graphical schedule editor. This editor allows you to define how the schedule value changes throughout the day. Activity schedules are often set as constant values, representing a steady level of occupant activity, while the occupancy schedule controls when people are present in the space. To adjust a value, click on the horizontal line and drag it up or down. You can also hover over a segment, type a number, and press enter to assign an exact value. For this exercise, set the activity level to a constant value of 100 watts. After defining the activity level, define the occupancy schedule that represents when the space is in use. Select the occupancy schedule and open its default profile in the editor. Several useful tools are available in the schedule editor. Double-clicking on a horizontal line splits it into multiple segments. These horizontal segments can be moved vertically or assigned a numeric value. Double-clicking on a vertical line deletes a segment. Vertical lines can be dragged left or right to adjust time periods. At the bottom of the editor, the hourly, 15-minute, and 1-minute options allow finer control over the time axis. Set the occupancy profile so that it is 0 between hours 0 and 8, equal to 1 between hours 8 and 16, and 0 again between hours 16 and 24. Notice that the light blue band next to the default profile matches the highlighted days in the calendar. This indicates that the default schedule applies to all days of the year. Additional rules can be created later to represent weekends or special days, but for now, this default profile represents the typical daily pattern, and in the next step we will add additional rules to handle variations such as weekends. Additional schedule variations can be created by defining extra profiles within the same rule set schedule. To do this, click the small plus icon next to Run Period Profiles. You will be given the option to create a new profile from scratch or copy an existing one. Copying from the default profile is often faster, since it provides a starting structure that can be modified. When a new profile is created, it is automatically assigned a priority number and marked with a different color band. Unlike the default profile, additional profiles include options for specifying a date range and selecting particular days of the week. This allows the schedule to vary between weekdays and weekends, or during specific periods of the year. For example, weekend days can be selected and assigned a schedule value of 0 to indicate no occupancy. More profiles can be added to represent holidays, reduced operation periods, or special usage conditions. Each profile has its own priority level, and when multiple rules overlap, the profile with the highest priority, meaning the lowest number, takes precedence. The calendar color coding provides a quick way to verify which profile is active on each day, and checking this visual feedback helps avoid scheduling errors. Next, duplicate the related schedule you created earlier and rename the copy to represent plug or equipment use. Modify the default profile of this schedule to reflect that equipment operation does not always perfectly match occupancy. This accounts for situations where devices remain on even when the space is temporarily unoccupied. The remaining schedules required for this exercise can be created using the same schedule editor tools. Now, we create 2 additional schedules to control the HVAC system. First, let's create the heating thermostat schedule. This schedule is of type temperature. For weekdays, set the temperature to 12 degrees Celsius from hour 0 to 8 and 21 degrees Celsius from 8 to 16. For weekends, keep the temperature constant at 12 degrees Celsius. Next, create the cooling thermostat schedule. You can simply duplicate the heating thermostat schedule and modify it. For weekdays, set the temperature to 30 degrees Celsius from hour 0 to 8, 26 degrees Celsius from 8 to 16, and 30 degrees Celsius from 16 to 24. For weekends, set a constant temperature of 30 degrees Celsius. Once all schedules are defined, return to the Schedule Set editor. Drag each of the individual rule set schedules into the appropriate fields within the set. This links occupancy, activity, lighting, equipment, and other operational patterns together under one coordinated schedule set. Thermostat schedules will be used later when HVAC controls are introduced. The other columns can remain unchanged for this exercise, since constructions will be inherited from the building or story level, and infiltration will not be included in this example. Next, select the Loads button within the Space Types tab. Let's create a new definition in the People section. Set the number of people to 1 and leave all other fields at their default values. Next, create an equipment definition. Set the design level to 310 watts and the radiant fraction to 0.1. Here, I've included the lighting energy use as part of the equipment load. However, you can define lighting and equipment separately if you prefer a more detailed setup. Now, go to the Space Types tab and create a new space type with an appropriate name. From the My Model tab, drag and drop the schedule set you created earlier into its place. Under the Load section, add the people and equipment definitions, and notice that the schedules you defined earlier are assigned automatically. Next, go to the Spaces tab. You can see the space we created earlier in the Geometry section, along with the thermal zone assigned to it. You can give it a suitable name here. Finally, from the My Model panel, assign the space type you created in the previous step to this space. Then open the Loads sub-tab to confirm that all loads and their associated schedules have been inherited correctly. You can also review the Surfaces and Subsurfaces sub-tabs to see that construction assignments are being inherited from the higher levels of the model hierarchy. In a simple building with only one space, creating a space type may seem unnecessary, since loads could be assigned directly at the space level. However, using space types establishes a structured workflow that becomes essential as soon as a model contains multiple spaces with similar functions. Now let's run the simulation and check whether everything we defined is being recognized correctly by OpenStudio. First, go to the Variables tab. Here, we want to track occupancy during the simulation. Add people occupant count as a time step variable. This allows us to see how occupant-related loads are being applied over time. Once the variable is added, switch to the Run tab and start the simulation. This may take a few moments, depending on your system and model complexity. After the simulation finishes, move to the Reports tab. Open the OpenStudio Standard Report, which summarizes the key results of the simulation. On this page, look for the Space Type Breakdown section. This view helps us quickly confirm that all the internal loads we assigned, such as people, lighting, and equipment, are correctly applied to the space type. Next, open the Annual Overview section. Here, you can see pie charts that show the end-use energy breakdown over the entire year. These charts are especially useful for understanding how much energy is associated with different types of equipment before any mechanical systems are introduced. At this stage, the results help us verify that our model setup is correct and ready for the next step, where we'll begin adding HVAC systems. As you explore the charts in the report, you'll notice that moving the mouse over each plot reveals the exact numerical values behind the graphics. If you want more detailed information, you can click the blue View Table buttons to expand the charts and see the full tabular data that the plots are based on. Another useful section is the Monthly Overview. Here, the monthly energy consumption remains almost constant throughout the year, with only small variations. These changes are mainly driven by the number of working days in each month, rather than by seasonal effects, since the space is still unconditioned. One of the most important sections of the report at this stage is zone conditions. This part clearly shows how internal loads affect the indoor environment. After adding occupants and equipment to the space, the results indicate a significant increase in the number of hours with very high indoor temperatures. In particular, the time spent above 88 degrees Fahrenheit rises dramatically, highlighting how internal heat gains alone can push the space into uncomfortable conditions. There's a benefit in some cases and climates, however. Those same internal loads slightly reduce the number of extremely cold hours over the year. But here, the overall thermal comfort clearly worsens. Humidity is also strongly affected. With occupants and equipment present, the simulation shows a substantial increase in the number of hours with relative humidity at or above 80%, which can have serious implications for comfort and indoor air quality. To better understand how these effects develop over time, we can look at a time series plot generated from the simulation results in D-View. Comparing outdoor and indoor temperatures over the same period makes it clear that internal loads are active during working hours and significantly raise peak indoor temperatures. In some cases, indoor temperatures are nearly 10 degrees Fahrenheit higher than they would be without occupants and equipment. All of these results confirm that, even in a simple model without HVAC systems, internal gains play a major role in shaping indoor conditions. This sets the stage for the next step, where we'll start addressing these issues by introducing mechanical systems and improving overall comfort. In the next stage of the workflow, we begin thinking about thermal conditioning. Before adding detailed HVAC systems, OpenStudio and EnergyPlus offer a fast and simplified approach called ideal air loads. An ideal air load represents a zone that is perfectly conditioned to meet heating and cooling setpoints, without modeling real equipment. In other words, the software supplies exactly as much heating or cooling as needed to maintain the desired indoor temperatures, with no limits on system capacity or performance. You can enable ideal air loads directly from the Zones tab. Simply check the Ideal Air Loads option for the zone. For this to work correctly, the zone must have both heating and cooling thermostat schedules assigned. Fortunately, these schedules were already created earlier as part of the space type definition. Drag the thermostat onto the zone, confirm that the Ideal Air Load option is active, save the model, and then run the simulation again. Once the simulation is complete, go back to the Zone Conditions section of the report. The difference is immediately clear. The hours with extremely high zone temperatures have been reduced dramatically. However, they have not been eliminated entirely, since the office is unoccupied at times, and the HVAC system is shut down during those periods. For now, we'll leave those settings as they are and focus on understanding the broader impact of conditioning the space. If you look at the annual overview and monthly overview sections of the report, you'll notice that the energy use profiles have changed. These charts now reflect the addition of heating and cooling energy required to maintain comfortable indoor conditions throughout the year. The monthly end-use breakdowns provide a particularly useful perspective. They show how energy is being used for heating, cooling, lighting, and equipment in a building that supports occupant activity. Reviewing these charts is an essential habit for any energy modeler. Results should always be checked to see whether they make physical and operational sense. One detail that deserves special attention is the presence of simultaneous heating and cooling during some months. This behavior is typically a sign of inefficiency. With ideal air loads, it often points to poorly coordinated heating and cooling thermostat schedules, rather than a problem with real equipment. You can confirm this by examining time series plots where heating and cooling activity are shown hour by hour. Seeing both systems operate at the same time indicates an opportunity to improve control strategies. As we move on to more realistic HVAC systems, issues such as simultaneous heating and cooling, unmet load hours, and frequent equipment cycling become even more important. At this point, the value of the simulation is not in producing more numbers, but in how we interpret them. Effective energy modeling is a structured, step-by-step process. We start by questioning the results at the annual level, looking for signals that do or do not make sense from an engineering perspective. We then move to monthly patterns to understand seasonal behavior, checking whether the model responds logically to weather, schedules, and internal loads. Finally, we rely on time series data to uncover hidden issues, control problems, unrealistic system responses, or modeling assumptions that do not reflect physical reality. This is where engineering judgment becomes essential. A simulation can always run, but it is the modeler's responsibility to decide whether the results are credible. By continuously questioning, understanding, and improving the model, we turn simulation from a black box into a reliable decision-making tool. As a practical exercise, think about how you could eliminate simultaneous heating and cooling in this ideal air load setup. Try adjusting the thermostat schedules, rerun the simulation, and observe how the results change.